We looked at conditions on the early Earth, but the conditions on our planet have not been constant since the emergence of life through to the present day. In fact, many environmental changes have occurred during that long period of time. We could look at a number of these, but let's just focus on one of them, which is of great interest to astrobiologists. And it's called the Great Oxidation Event. It's that period in Earth history when oxygen rose to levels that we're familiar with today. In fact, it occurred over more than one period. The rise in oxygen turns out to be very important for life because oxygen enables aerobic respiration, a very efficient way of gathering energy. Where did the oxygen come from? Well, the early Earth had less than 0.1% of the oxygen we have present in our atmosphere today, and we'll look at the evidence for that in a little while. It raises several questions of great interest in astrobiology, and here are some of them. When did oxygen become abundant? And what was the cause of the rise of oxygen? How do we actually track the rise of oxygen? How do we know it increased, and how do we find out when it increased? And how did the rise in oxygen affect conditions on the Earth, particularly conditions for life? Let's look at some of the ideas for answers to these questions. First of all, when did oxygen rise? And what were the periods of the increase in oxygen in the Earth's atmosphere? This is a graph showing the concentration of oxygen over time. And on the x-axis at the bottom there, we go from the present day on the right back to the formation of the Earth over 4 billion years ago on the left. And you can see the red line tracks oxygen through time. In the early history of the Earth, oxygen was less than 0.1% of present. And we can tell that by what we call proxies. These are geochemical signatures in the rock record, types of rocks that can tell us that the oxygen was within certain bounds. We'll come back to that evidence in a bit. And then around 2.4 billion years ago, oxygen rises to something like 5 to 18% of present levels, and it stabilizes there for a long period of time. And then between about 600 to 800 million years ago, there is a second rise in oxygen that leads to the oxygenation of the oceans and leads to oxygen concentrations that we're familiar with today, around 21%, although it has varied during that time. What caused the great oxidation events, particularly the first one 2.4 billion years ago when oxygen rose from very low levels to something like 5 to 18% of present day? Well, first of all, we have to understand both the sources of oxygen and also the sinks for oxygen, the places where oxygen disappears to, how it's removed from the atmosphere. The sources of oxygen are photosynthesis. For example, plants and cyanobacteria, microorganisms that produce oxygen as a result of photosynthesis. Oxygen is a waste product of photosynthesis, the metabolic process by which organisms get energy from the sun to build complex carbon molecules. Photosynthesis, at least oxygenic photosynthesis, produces oxygen as a waste product. So that's the main source of oxygen. That's how oxygen would have been pumped into the atmosphere from photosynthesis. How does oxygen get removed from the atmosphere? There are really two main mechanisms by which this happens. The first is that when organisms die, their organic compounds literally react with oxygen, consuming oxygen in the atmosphere. But if those organisms are buried before they can react with the oxygen, then they don't have a chance to remove oxygen from the atmosphere, and there's a net build-up of oxygen in the Earth's atmosphere. So burial of organic material, burial of dead organisms can help oxygen build up in the atmosphere. Another way in which it can be removed from the atmosphere is by reacting with volcanic gases. For example, oxygen can react with hydrogen sulfide or methane, and in the process get removed from the atmosphere and result in lower oxygen concentrations. So if we want to build up oxygen in the atmosphere, one of two things has to happen. Either less of it must be taken out of the atmosphere, or more of it has to be produced. So why did we get this abrupt rise in oxygen about 2.45 billion years ago? Well, some possible explanations are that there was a sudden decrease in the elements or gases that react with oxygen being produced, for example, by volcanic eruptions. This would have led to a net build-up of oxygen in the atmosphere. Another explanation is that photosynthesis evolved about 2.45 billion years ago and produced oxygen that built up in the atmosphere. However, the rock record and the phylogenetic evidence suggests that photosynthesis is much more ancient than 2.45 billion years. So we think that photosynthesis was occurring long before the Great Oxidation event. That doesn't look like a particularly good reason. Another reason could be an increase in the burial of dead organisms. Less of the organisms were around to react with oxygen in the atmosphere and remove it, and as a result, oxygen built up in the atmosphere. It could be that some of these conditions occurred in combination, and that there was a switch between two different stable conditions. A stable condition in the Earth's environment where there's very low oxygen, and another stable condition where there's high oxygen. And at some point, 2.45 billion years ago, the Earth flipped between those two different stable conditions. However it occurred, whatever the reasons for it, it had profound consequences for the Earth's environment. A rise in oxygen would have mopped up methane, and methane is a greenhouse gas. So as oxygen rose and it mopped up this greenhouse gas, temperatures on the Earth would have reduced, and there would have been a period of cooling. In fact, there is evidence for glaciations following these great oxidation events. The production of oxygen also would have changed the chemical nature of elements on the Earth's crust, and so changed the chemical cycling of carbon, nitrogen, sulfur, iron and other elements essential as nutrients for life. It would have radically changed the biosphere and the accessibility of nutrients to supply the biosphere. For life, the increase in oxygen was a double-edged sword. Of course, for those microbes that were living on the Earth before the rise in oxygen, they were adapted to anaerobic conditions, conditions without oxygen. The rise in oxygen would have been fatal for many of these organisms, and they would have had to have persisted or been confined to anaerobic environments, such as, for example, deep ocean hydrothermal vents at the bottom of the oceans, or other areas, for example, in the crust, where reducing conditions would have maintained anaerobic or oxygen-free conditions. But the other side of this is that oxygen would have allowed for aerobic respiration. Aerobic respiration is about 16 times more efficient as a method of generating energy than anaerobic means of growth. It allows for complex behaviors, even running a brain. And so the production of oxygen at high concentrations in the atmosphere may have led to multicellularity. It may have led to organisms that were able to use oxygen as a way of gathering large quantities of energy in order to grow and reproduce. Another way in which we can look at past oxygen levels and try and understand when it arose was to look at phylogenetics, to try and understand when the first organisms appeared that might have been responsible for this rise in oxygen. For example, cyanobacteria, once called blue-green algae, are a group of organisms that are photosynthetic and produce oxygen. We now know from phylogenetics that cyanobacteria were very deep branching, and that means that they appeared on the Earth a long time ago, probably a lot longer before the Great Oxidation event, and they would have been responsible for producing oxygen in the Earth's atmosphere. Indeed, they might explain why there appear to be episodes of oxygen production even before the Great Oxidation event. Photosynthetic microorganisms might have been producing oxygen well before 3 billion years ago, but this oxygen they were producing was being mopped up, for example, by gases produced by volcanic eruptions long before the Great Oxidation event. Another way in which we can track oxygen in the rock record is to look at particular minerals that are only produced at low oxygen concentrations. Here are just some examples. For example, pyrite is iron sulfide. It's a mineral that's only produced at oxygen concentrations much less than 0.1% PaL, present atmospheric level. Uraninite is a mineral of uranium oxide, that's only produced at oxygen levels much less than 0.01% present atmospheric level. And siderite, which is iron carbonate, is a mineral that generally is only produced at oxygen concentrations much less than 0.001% present atmospheric level. So if we find these minerals in the rock record, it tells us that oxygen levels were very low at that period of Earth history. And this is how geologists have managed to track the history of oxygen throughout Earth's history, by looking at these minerals in the rock record and by inferring the levels of oxygen that must have existed, very low levels of oxygen, for these minerals to have been able to form. Another way in which we can track oxygen through Earth's history is by looking at elements that change their solubility in water, the amount they're dissolved in water, depending upon the amount of oxygen in the environment. And the depletion of certain elements from ancient soils or paleosols can be used to infer the oxidation state of the atmosphere. For example, under very low oxygen conditions, iron is very soluble in water. And generally in rocks before about 2.4 billion years ago, we see very low levels of iron and an increased levels of iron after about 1.8 billion years ago when the Earth was more oxygenated. Some of the most remarkable features in the early rock record are banded iron formations. These are thick geological deposits containing a high abundance of iron oxides, essentially rust. How did they form? Well, one theory is that the early oceans contained very high concentrations of dissolved iron, which would be the case if the ocean had very little oxygen in it, in an environment that was essentially oxygen-free. Every now and again, this iron would have been circulated through the oceans and it may have come into contact with more oxidized surface waters in the ocean. The iron would have oxidized and it would have settled out in the oceans and formed these thick geological deposits. These banded iron formations are widespread early in the rock record before about 2.4 billion years ago, before the Great Oxidation event, but they essentially disappear after this time. And so these banded iron formations are evidence that high concentrations of dissolved iron were caused by low oxygen conditions on the early Earth. So what have we learned in this lecture? What we've learned is the levels of oxygen rose rapidly about 2.4 billion years ago in the Great Oxidation event. The cause of this rapid shift is quite ambiguous, but nevertheless, however it occurred, the rise in oxygen had a significant effect, probably on global climate, as it eliminated the methane greenhouse effect. The increased oxygen is thought to have facilitated the rise of complex multicellular organisms. And finally, the interpretation of the rock record is really key to our understanding of the history of oxygen in the Earth's atmosphere.